in the context of the infrastructure information, the big relation, the high every single thing that I have why not keep relations?
Hey guys, I'm sorry, a little late. I'm almost never late, but you'll see more of it. I apologize in advance. In return, I will allow you to be late as well, most of the time. Favor. So today, remember we did this introduction. We kind of tried to understand what operating system is. Let's quickly, I'll quickly talk about it again a little bit more. But today our topic is, which probably will take us 2 lectures because it's a slightly longer thing, is how to design an interface of an operating system. And we'll talk about like different design ideas, but then we also will try to understand how a Unix interface works. Let me quickly, I wanted to just, man, how do I really need to quit? Sure, I can't quit. I wanted to like come back to that figure which I was drawing last time, which is, of course, not this one, maybe this one, right? So remember, I talked and I said, okay, what is an operating system? And the main thing which I wanted you to remember, like for the duration of this class, and maybe hopefully for the entire like rest of your career, is the following. So the main observation which I was trying to push on you is that the CPU itself, any CPU which you take, is reasonably simple. Remember this fetch, decode, execute loop, right? So a CPU just blindly executes instructions like one by one, whatever is there in memory. Sometimes there are jumps or even else like essentially comparisons and jumps. Sometimes there are jumps backwards, stuff like that. But everything is reasonably like kind of flat, right? It's just an instruction tree. And it's important to understand. And suddenly, when we take an operating system, like, for example, a phone or a laptop, right? We see a bunch of windows. So it doesn't seem flat. It seems like there's a lot going on, right? And we see those windows and everything is jumping at us very, very fast. The question is how, right? And this is, again, my main point, which I'm trying to do, is that this, like, if I start drawing something like windows on a screen, which are also overlapping or something along those lines, right? Those are windows, and this is the entire screen. I mean, I used to draw better, actually. The question, like, what is this connection between this flat world and this kind of multi-dimensional world? I'm not even talking about VR, but it's kind of the same idea, right? So do you guys know how it works? So what's this gap between flat instruction by instruction and multiple windows which are jumping to you? What is happening underneath? Does anyone know? Switching, yeah, exactly. And so that's what I was trying to say, that, you know, if you start with an operating system and it executes some instruction stream, so let me just create a little bit more space here. I'll be drawing operating system as black for now. Like, imagine this is where you power on your machine. And it, like, the CPU designers give you a manual and it says, okay, when you power on, I will come back in this specific state. In practice, it's so complicated that sometimes us, like on Intel CPUs at least, there is so much magic going on in this early stages, not of boot, but initialization of the machine, that we can't even do it ourselves. Intel gives us like binary blobs and says, run those and everything will be fine. We'll initialize memory, caches, everything for you. Well, not ideal. We have to trust this code. But okay, imagine a simpler CPU and everything is fine. And you start booting and you reach at some point main, which I was trying to, like a function which you can implement in any language which you like. There are operating systems written in Java, Rust, obviously, C, C++. I would say any language you like. Go. It's possible. So the language is not a problem. Like you can write it in any language. I run this class in C because it's, I would argue, the easiest. It's not maybe the easiest to program, but it's the easiest to understand what's going on. And then you start like, again, operating system does something here. But the core thing which it does, and this is what I was trying to explain last time, at some point it loads another application in memory. Typically, you load from disk, but again, it's not given. You can load it from anywhere. Maybe it's already in memory because earlier stages which were involved in boot somehow got it. Maybe it sits on your motherboard in some non-volatile memory on the motherboard and comes back every time you turn machine on. So BIOS works this way. BIOS is a piece of software which runs early on stage, on boot stage. And then operating system switches and starts running this. I'll show it as green. And green stuff runs for a while. Like this is some app. And then either green says, okay, I'm done running. And it like yields the CPU voluntarily. Maybe it says, okay, I want to read a file, or I'm waiting for the next network packet. And it just says, okay, I don't have anything to do. Like, please run something else. Or as I was trying to explain last time, a hardware primitive, a timer interrupt, preempts execution of this green application. The operating system starts running again for a while. Typically, it's kind of like sharing a resource, right? So I wanted to say sharing a bike. When you're a child, you say like someone gets a very new bike. If you're an adult, it's like a carbon fiber or something, the lightest, the newest, and everyone wants to ride it. And you come up with some policy, who rides it next, right? Or we sharing the rooms in the university, right? And so here, operating system makes a decision. It's called scheduling. So in practice, what you're trying to achieve here, like literally, operating system tries to pick the next program to run, enforcing some fairness. And definition of fairness can vary. It can be maybe everyone gets an equal amount of time on a CPU, each application, which seems that it's as fair as it goes, right? In practice, you might want a different definition of fairness because you say, look, one application shows me really something important. Maybe it shows a movie. And if I see a lag in a movie, I'm really upset. So a movie running application maybe should get more CPU time, right? So in some way it's unfair, but it's maybe what you want, right? So the scheduling decision is some logic and you just program it. Remember, kind of like you're still running inside your main function. So you can implement this logic there, right? And I will show how to do it. And imagine you pick the next application, like I'll make it blue for now. Then you switch back to this blue one and blue starts running for a while, jumping around. But again, everything is flat. Like inside blue, it just jumps forwards and backwards, infinite loops, whatever you guys program. And then again, maybe a timer or maybe a yield, like preempts execution of the blue. And then I wanted to say orange, but maybe for the illustrative purposes, we exit into the operating system. Again, make a scheduling decision saying, okay, what is it we're running next? And maybe we're back to green again, right? So switching back into green application, right? That's how it works. Everything works this way, right? And it doesn't look very, very sophisticated, right? So you're just switching between applications. And typically, those periods of time, they vary. So for desktop systems, we typically pick something like 10 milliseconds, maybe up to 100 milliseconds. Then humans are still fine. Servers typically configure to run at 100 milliseconds because why is it a trade-off? Like why not to run for just 1 millisecond? It's fine, but then every time you do a switch here, right, you pay some amount of, like it's an overhead. Maybe there is like, instead of like spending like, let's say 50 or like 5 milliseconds or something, maybe less than 5, like let's say 0.5. Inside the kernel, you could have done something useful, right? Instead of picking the next application to run. So this interval for how long to run is, again, is a choice. And depending on what you're running, the workload you're running, if it's a data center and you're running Facebook, like memcached, then may choose like a longer interval because nothing else is running on that machine. If you're running a desktop, you choose like a smaller interval, right? But again, reasonably simple. So if I kind of bet that if I lock a couple of you in a room for half a year, you will write me this, right? So even without any education. But my goal, obviously, to help you to write it faster within a course of one semester with less pain and just like a couple of hours a week, right? But any questions about this kind of conceptual figure or like overview? Good. Yeah, very, very simple. And I'm like, okay, question.
The scheduling, is it a function? Something? Does it have a name?
Yeah, it's a function. So typically, if you think about it, schedulings, you say, look, I have a list of processes in a system. Like you can maintain that list as a linked list, right? P1, P2, P3, and so on, in the order of creation, or some order, right? And you say, like, what's the simplest scheduling policy? What you probably know it already. So what is, like, if your schedule function, which you write in C, you say, look, I will take a pointer to the beginning of the list or something like that, right? That's an input. And then you say, look, what's the simplest policy you can imagine? Well, that's almost the simplest, but it's actually in practice, you will be surprised how hard it is to implement. Because what if this guy, you say, I'll give it like, let's say 100 milliseconds to run. But this guy exits early after running 30 milliseconds because it says, I want to read a file or I'm waiting for a network packet. And then it comes back later and says, okay, I didn't finish running. It's my bike. I mean, I took lunch, but I came back and I want to ride it. And that becomes tricky. So the simplest, arguably, which one? Do you guys know? Anyone? Yeah, just go through them in order, like fairness, unfairness, just pick the next one, right? So, and you say, look, I will just always pick the first one and I will put it maybe at the end of the list. And that's about it. And if you finish running early, well, your problem. Is it fair, unfair? Hard to say. Like, but you say, look, but what about those high priority applications, like, for example, video players or something, right? And then you say, look, I want a more complicated data structure, which accounts for priorities and stuff like that. And at this point, it's more like an algorithmic task. So it's not like really operating system class. You say it's operating system class, but it's nothing exotic. You say, look, I will come up with some kind of a tree which sorts them according to spent time, and then it will remember how much time is left, and it will, maybe it's both a tree to retrieve it fast and a list, and then you don't insert at the end, but you insert in the middle because you say you will have more time to run, stuff like that. But in reality, just as function, and we'll take a look at how it's implemented, right? Any other questions? Okay, there's a couple of things. First of all, it's a great question. So the only hardware thing here is this. The fact that I made a label here, the code which implements context switching runs on the CPU. It's all software, right? The only hardware primitive which we need is this special way of preempt execution, which is done with a timer interrupt. And I will cover how it works. It's just important to understand that everything what I'm drawing here is software, right? And you as a system designer or student in this class can build it in your operating system, right? Now, the second question was, what happens if you simply run one process, right? And we talked about it a little bit last time. like Arduino, I don't think it implements context switching. First of all, I'm not an expert on Arduino. I just programmed it a couple of times. But what it does, it just literally says, okay, we have this infinite loop, like the whole program. We boot into your main function, and it's you after that. You may want to implement some kind of a context switch, but really we will just expect you to run a polling loop. And you periodically inside this loop, you say like, read the sensor, read sensor 1, and do something, read sensor 2, and do something. If you want to prioritize sensor 1 over sensor 2, you're kind of on your own. This is where like Arduino starts breaking. And this is where you say, look, I want to run multiple threads. Like maybe this guy will be running its own loop, and this one will be running its own loop. And maybe this will be running for twice as much CPU time because I care more, because it steers the wheels and I don't want to crash my car, right? But that said, even on mature operating systems in data centers, why this question makes sense? Because modern systems are not like a one CPU and you run something. Like modern systems are data center scale. You have tens of thousands of machines potentially running the same application, be it Netflix, streams files, be it Facebook, caches, and whatever, builds, whatever, referencing, whatnot. And you say, look, we observe that we can run faster if we avoid context switching or as much as possible. And then you say, you can also optimize existing kernels to kind of, and it's still kind of a research challenge to avoid as much of this context switching as possible, although typically there is still some. So that's a design choice people have to make even today. Any other questions? But we got how it runs, at least at high level, right? I just wanted to ask a question still, coming back to those windows. Do we understand how we get those windows on the screen in the end? Like, it's nice, we have blue, we have green, but I just wanted to make sure that there is no magic and we understand how the windows show up on the screen. So how does this work? Do you know?
Is it because the context switching is very fast? So...
Yeah, it's very fast, and you don't notice. But what I'm trying to ask is kind of somehow, imagine my kid comes to you and asks, okay, look, Daddy, I have windows on the screen. What's going on? You're talking about those computers. I don't get it. I don't care to be what I say, what I scroll like crazy, right? So how does it work? So I just wanted to give an overview to make sure that we understand how it works. More or less correct. I mean, in fact, correct. Let me just make another drawing. So just wanted to make sure that we have this picture in mind before we do anything. Like, again, back to this thing. So my operating system is running, switches to something. And this something can be a special application, which we typically is called something like a compositor. So compositor is a piece of software, which is a regular process, which runs on your like system, right? It also takes a slice of a CPU time to run for a while. The way it works with the graphical screen is that if you have something like a real like LCD panel, first of all, this LCD panel, like it has some kind of like pixels, right? Whatever, like that's pixels. It will have a tiny microcontroller here, which will also run a tiny operating system, most likely. You will never hear of it, but it will be there. Maybe it will run this like infinite loop, and that's about it. Maybe there will be no context switching. And in practice, how it's connected to the machine is that modern interfaces allow you to, if this is a DRAM memory, in practice, what the compositor is doing is just writing some information in a special region of memory here, which is called, let's say, for simplicity of it, a frame buffer, although it can be more complicated. And like there is a collection of buses which connect the screen, whatever, this tiny logic here, and allow it to kind of read this memory. So essentially this code here reads the memory, and you say like, okay, pixel number 1, well, maybe it's whatever, green, for example, here, right? Pixel number 2 is blue, something like that, along those lines, right? So communication goes through memory, roughly speaking, although it's not really entirely correct, but like it's correct for most things. But if you're using a GPU, then you ship this memory to the GPU does something, then it just like ships it back to memory, and then another piece of hardware shows it, right? But essentially, compositor, the logic of this compositor is that if you're running multiple GUI applications, those graphical user interface, like applications which want to show some windows, which have a window, they will have their own regions in memory to represent their windows. Kind of like it says, okay, my window, I'm streaming a movie, that's like me running around on the screen, right? And this one is maybe a code editor, which types something like hello, right? And it's all in memory originally. And compositor just can read this memory because those memories are accessible to the compositor, and it decides, okay, one is on top of another, and it essentially composes a final figure for what to be displayed on the screen. So when you have a person on top of a hello saved in this memory first, and then this combination of software and hardware reads it from the frame buffer and shows it on the screen here. And you will see a human on top of a movie on top of a text editor, right? This is easy, right? It's kind of like 101 stuff. So easy that you got distracted, right? But we understood it, right? And because everything is switching so fast, we as humans don't even notice, right? And sometimes we have multiple CPU cores. Moreover, it runs on multiple cores in parallel, more power. The windows are moving even faster. And every 2 years, we have to buy a new laptop just to run even more windows, right? Good. Overview is done. So this is an operating system, right? So you just have to build the piece of software which does this context switching and does something like access to hardware. That's typically called, this access to hardware is called device drivers. So it's just pieces of software which abstract, instead of like expose low-level layout of a frame buffer, it just says, okay, like write a pixel in a position XYZ, and it will do it for you automatically. Any questions on that?
Which parts in in scope of this course? The driver, the compositor, also in scope.
More or less everything.
Everything.
So, and that's the reason I want to talk about it. So we will not, like, x86 has a primitive graphical user interface. It only can print console, like letters, hello, on the screen. And it doesn't have any like GUI, which allows you to draw lines or anything like that, right? But still, you can take a look and say, look, how does it work? And you can read the source code of x86 to see like how actually there will be no real compositor there, but there will be a function which puts something in a frame buffer, and then it shows up on a screen. And it will be in your homework as well. There will be some primitive device drivers, and x86 comes with a very primitive device driver for disk. It doesn't have network. We might build one, we'll see. Never build it, but we'll see. Also, I forgot to mention, we all know files, right? And this part of the system is called file system. So that will be also in scope. Scheduling will be in scope a little bit. Allocation of resources and managing of memory, which is memory allocation, right? So malloc and stuff like that is in scope. Loading of programs in memory. So this step of first loading in scope. Timer interrupt management will cover it. Context switch will cover it. So almost nearly everything. It will be simplified because x86 on its own is simplified. So just to make sure that we can finish. And in fact, I will like try to move a little faster because I was running out of time of something. I'll change priorities, making sure that we cover something else compared to previous year. Good. Done with an overview. Not hard, right? So again, that's my goal is to just to make sure that like we understand all of it in some concrete terms. Okay, now I'll switch to a slide deck here, and my slide deck will look like this. So this is again, if we took a if we take a look at an operating system organization, right, it will consist of, roughly speaking, the following components, right? So here at the bottom, I will be drawing, in my class, it will always show up as yellow. So, and it's called the kernel. Someone mentioned this word last time, right? So it's the most privileged part of the operating system. It boots on bare metal. It's where you boot the machine. Your main function sits here. So this is where your main function is. But all the other parts like scheduler, file system, if you have a network stack, there will be a network stack, virtual memory management, and in general memory management. Everything sits in this stuff, right? Moreover, this part of the system runs in a special privilege level. So it's more privileged than others. It's on Intel, it's called ring 0. Intel implements a notion of protection rings, and there are 4 on Intel, but only 2 are used, ring 0 and ring 3. So user applications are they run in ring 3. I will explain what these rings are. In fact, we'll create those rings, right? Because many operating system classes will just skip over it and say, look, there are 2 rings, but what those rings are, since we will be booting on real hardware or like emulated hardware, you'll have to get those rings right. Don't worry. So I will explain them. And on top of it, of course, we run user applications like whatever, Shell, Apache Web Server, stuff like that, right? And those will be like green and blue in my class. The reason, why do you know why we run those in 2 different rings? What is the point of this?
Privileged access to memory, so you don't want your Apache web server to be able to mess with memory that EOS is using.
Correct. What you're saying is isolation. And I was trying to talk about it last time. But in practice, and it wasn't always the case, and it's not always the case now, but it's becoming more and more the case, up to the point that almost, yes, it's always the case. We don't trust individual applications. Why? Because typically on a single piece of hardware, you're running applications from multiple vendors, which have slightly different incentives, right? And some of them try to steal your personal information, like credit card information, and just sell it, or just make a transaction in your name, right? From your bank account, right? And essentially, everything what we run today, each application is kind of like running in a tiny little cage, which is completely isolated from the rest of the system. There will be like, think of an airport and a TSA. They can enter the kernel through a very narrow interface of system calls. And here we will do a bunch of security checks, and we'll take a look at what those checks are to make sure that the system call is not trying to break the system. But logic is clear, right? So if you downloaded something from the web, especially 2 web applications. One is your bank account, another is whatever, your video game, which you downloaded from a dodgy site and somewhere on the web. Then who knows, maybe that thing is trying to steal your credit card information, right? And well, like when I was a student, it wasn't that sophisticated, but today people learn how to exploit or attack systems, figuring out bugs in code, which can lead to like the case in which like the attacker controls the system completely, right? But sometimes the most extreme case when the attack is remote. So you send a network packet and suddenly you own a machine on the other side of the world in some other data center. It still happens today, right? And it will be happening for many years to come, right? But essentially the idea is that each application is isolated in its own little cage. So they cannot access memory or like any other state of each other unless there is a bug, which is possible. And they cannot access operating system, right? So that's why we have those privilege rings, right? And so the operating system will be responsible for setting up those cages or like isolation boundaries to make sure that applications cannot access each other, right? And like, I mean, I don't know if you thought about it, but everything what you're running is running in those isolation boundaries, right? And in fact, like different web browsers choose different isolation boundaries, and it's a trade-off: performance versus isolation strengths. You know, someone runs each web page in a separate process. Some other web browsers do different things, and sometimes there is isolation even within a page, within this one little process, there will be something as well. Okay, we'll get back to it, but okay, so this picture is clear, right? So just wanted to make sure that this picture will be coming back, right, over and over. And operating system like talks to the device drivers. There will be some, like, for example, network stack. They will be running on top of like network device driver, net driver. And this will be talking to hardware, very similar to how I just described the compositor. There will be a region of memory shared with a piece of hardware, like shared with the hardware attached to a bus, which will be able to read this memory. And this will be a communication interface between the operating system and the device itself. And again, don't be surprised that the device itself will run some kind of a CPU. Today, it's probably kind of some kind of an ARM, but often quite powerful today with a proprietary operating system, which they will not tell you what they're running, but they will be running an operating system on those devices, right? On the network, on the disk. Even the CPU itself will be running an operating system. Yeah, it's kind of like a fun, and not one. I mean, like technically speaking, just maybe two more. Like Intel CPUs run two, I would say two more operating systems underneath, and they never mention it to you, but they are there. Like, I don't know what macOS does. I know that they run at least one more, but Intel does too. One is running in Intel management mode. We'll talk about it. And one is BIOS, which is like also running underneath. Okay, cool. So this is clear, right? This picture. Again, kind of like still very, very slow, very, everything is rosy right now. Don't worry, our gradient of like information will go up very, very quickly. So, and we got like, I was setting up the stage. It took me like 40 minutes. Our topic of today's lecture, after we understood what we want to build, at least at some level of details, imagine you're skillful enough, you can build whatever I described, device drivers, schedulers, context switching, timers, for a second. And by the end of this class, you will be able to build. But imagine you're a designer and someone says, okay, can you build me a new operating system? I want to run XYZ. The question is, what this interface should look like. If you think of a library, like imagine you have a data compression library like zip or something, gzip, right? You say, look, maybe I have to implement two functions, whatever, inflate, deflate, encode, decode. And you as a designer, probably most of you done it in your life already, especially if you work for a company. They tell you, okay, we want a library which does something, I don't know, sorts list, but very, very fast and very, very big lists. And you come up with an interface how to do it, right? At some point, you have to come up with an interface for the operating system itself. And it's a topic of our like today's and tomorrow's, not tomorrow's, but next week's lecture, next lecture. But if I ask you a question, what do you think this interface should look like? You as a designer, like starting from scratch. I did it myself a couple of times in my life. Sometimes I only did the interface and never built the operating system. I failed, but still it's a fun exercise. So think about it. So what should it do? Or what it should look like?
Some arguments and when the operating system do the context switching, it can do something to the application.
Well, let's be more concrete. Like, let me give you a hint. So your very first task, as I was going through this introduction, was you want to load applications and start running them, right? Sometimes maybe there is no context switch, like your classmate said. That person said, okay, like, what if I don't want to context switch? Totally, like, I just want to load the application, right? Maybe it's one. Maybe you need context switching as well. But let's start with loading. So what is it we need to load an application or something? What the interface will look like? Correct. So, but it's more like maybe what you're saying is that if this guy has main, my goal when I start running, I want to make sure that instruction pointer points to main, right? But it seems like more like a low-level detail, which will be sitting somewhere in the operating system here. Like I would even say close to maybe something like next to the, yeah, when you create a process inside that call, which says, okay, create a new process, you will set instruction pointer to the main. But from the point of view, like if you're thinking, I gonna, yeah, exactly. Then what will be, the call will be, yeah, you can come up with some kind of a function call which says like create a process, right? And what will be the argument to this create process call?
File path.
Yeah, a file. So you can say, look, and I will have it in somewhere like in slash something slash whatever cat, for example. That's nice. You say, look, my operating system will be able to create new processes with this create process system call, right? And internally, you will implement it. It will like, if your process is an ELF file, I will explain what this ELF container is, which like the de facto container to keep executable files on Unix machines. Internally, you will pass the ELF, you will load it into memory, but like the interface will be create process, right? Which takes a file, totally fine. I built a couple of operating systems which had this create process. You say, well, but my applications need to do something. So along with create, you probably need a couple of other things like maybe kill or destroy, I don't know, like because you say like, if this one is running for too long or takes all my CPU, I won't be able to terminate it, right? So let's say terminate. So create and terminate. That's more or less enough to start, right? Inside the process, if you're coding the, like you say, look, I want to do something useful inside my process. What kind of set of system calls you need inside? Like think of like, I don't know, like anything useful, the minimal useful job you want to do. And what? Allocate memory, right? You say, look, I want to be able to allocate memory. So my second most important system call will be something like malloc and or mmap, depending on how you want to think about memory. And I don't want to be very specific here because there are multiple design choices you can make, but let's say allocate memory. That's a great, yeah, so that's most important because in practice, you can't even like start running your main because, I mean, we will talk about it, global data, local data allocated on the stack, and what is it, dynamic data allocated on like convert or on memory allocated by the malloc, but you can't go away too far. I mean, you can, but it requires an extra effort if you want to avoid malloc and everything is global. But yes, malloc is needed to like even run some kind of a libc or anything, right? Okay, cool. We have create process, allocate memory. That's good. What else? Exactly, right? Even like the very first operating system I did write, like I wasn't writing it, but it was a crypto device. The crypto device was designed, I was in Ukraine working for a company which was protecting digital rights. So if you stream a movie, it will not decrypt the movie unless you plug in the specific like a USB attached crypto device with a key, which then decrypts the movie, and we change the key every so often. On that device, you say, look, I want to keep the key in memory. Maybe I want to keep multiple keys. There is no context switching, nothing like that, but you really want to have some kind of abstraction of a file system. As a human, it's much easier to program because you say, I have non-volatile memory on this device, and I say 1 key, 2 key, 3 key, but then the mass comes very, very fast. And you say, look, I want to give them names, structure them. You say there must be some kind of a file IO, file interface. So, and this file interface should be something like open, like create if you have a new file, maybe read, write, and close, right? Agree? And then you have files, and you can go along with this. I would also say you need something to put something on the screen or on the network. And that's a little bit more complicated because you need to come up with some interfaces to do like graphical user interface, or at least the console. And for the console, you can just say, I'm going to be writing at some specific special files. And those files will be redirected on the screen. And that's totally fine, like standard input, standard output, right? If you have a network stack along with files, you should come up with some collection of system calls to access the network stack, but kind of like open a connection or receive connection, send, receive, right? Close connection, whatever TCP/IP has bind and stuff like that, right? What else? Do we need anything else to run? I kind of tend to believe that that's more or less it. So if you want to build a very minimal operating system, which you want to build, like remember my last time I was talking about this wearable device, which was registering the UV light, you're kind of done at this point. So you don't need anything else. And I argued that never build anything extra until you need it, right? But that should be fine. So this is the interface, right? Agree? Okay, good. We brainstorm it, but let's take a look at how, I mean, first of all, I wanted to say, there is no single, like the best interface. Why is that? Because like your target applications are changing every, like say 5 to 10 years. We used to run everything on, I have a slide here. I will show it to you later, but let me just jump ahead. Where is it? Oh, lost this one. So we used to run everything on those machines, which had like a keyboard and a printer, which brings something back. Then we moved to something like, terminals. This is not a computer. So it's just a screen which shows the characters and the operating system, and it's connected through a modem to an actual computer, which sits at the university or at your work. So it's just like a smart glorified modem which talks to a machine which runs elsewhere. Machine is way more expensive. This thing is cheap, but that's how it was, right? And then we moved to like personal computers, phones, and then we moved to warehouse computing. So now we run data centers, right? And the interfaces will be changing because you have different like requirements for what is that you want to do with this interface, right? And there are different ecosystems, like Windows chose a different set of interfaces versus Unix, versus, I don't know, some exotic operating systems which run in the embedded space. If you like program a car or something, then you will, or like whatever, an insulin pump, there will be an operating system which will have a slightly different interface. But at a high level, they all have those components, which we listed here on the screen. We will cover the Unix interface. I'm not saying it's the best. In fact, it's a little exotic, and it has like this combination of a fork exec, which a normal person cannot think of. But they did it, and it's kind of survived for like whatever 40 years. So it's probably not the worst. It's not the best, but nevertheless. Okay, so we're going to be talking about Unix interface and essentially what we're running on Mac OS, Linux. Windows has a slightly different one, and they're struggling actually. Okay, so system calls, this layer which implements interface of the operating system, right? And we already talked about which system calls we need. So create a process, terminate a process, read file, send something on the network, stuff like that. And that's what I have here on the slide. One thing which we missed, remember compositor. We said that compositor can talk to other applications. We never talked about it, kind of. I said that each program runs in a cage, right? In practice, they can set up communication channels and communicate with each other. On Unix, it's done through an abstraction of a pipe. It's not the fastest, maybe not the best, but there must be something what allows programs to communicate. Just remember this compositor, because remember each application has its own window. They send these windows to compositor. Compositor says, okay, like I know who is running on top of whom, and I will compose them, right? So there is this ability to communicate between programs, right? But we covered everything else, like processes, memory, files. So pretty good. So we understood how it may work. So on Unix machines, which were like this interface, remember I said that everything is the interface of the operating system is driven by what you're actually trying to run on those operating systems, right? And if you're running in a data center, like maybe you programmed AWS, roughly speaking, there will be an interface to the cloud, right? And that's your kind of maybe operating system interface at this point. I didn't do anything. But on Unix machines, everything was built around this program, which is called a shell, right? If I ask you a question, what is a shell? Do you guys know? Well, like don't think of it as some kind of a tricky question, but at a high level, what is a shell? It does talk, but it feels to me, I kind of agree with you, so I cannot disagree, but maybe there's someone can give a better definition. Interact more directly with computer. But you know, like keyboard is also a way to interact with a computer, right? So, and if you take a phone, here I'm like using my finger, right? So it's also a way to interact directly with a computer, right? A shell has a slightly like awkward flavor, which, I mean, you use this flavor every day, but what kind of flavor it has? Anyone can guess? You type, but it's not like you just, you can also type into ChatGPT, right? And it will also do something, right? What I'm trying to get to is that shell implements a somewhat very primitive programming language, which allows you to compose things, meaning that you're absolutely right. So it's a low-level interface. Let me quickly maybe switch to shell here. It's our, oh, I didn't switch because this thing is on top. Let me just quickly go back and stop the slide deck. Just wanted to show, man, that is correct. This, apologize. So like, I can do something like, ls will show me all files in a folder, right? You say, wow, you're smart. That's very useful. We all understand it. I can switch to a different directory here. I can go up, can go to my home directory, do ls there. Let's not do it because who knows what's there. But stuff like that. I can also read files like I can, whatever, ls here. Let's go here, for example, maybe ls. I can cat on a to-do, right? And it will show me that it's empty for now. That's very smart, but it's empty. So I interact with the computer, right? But it can also do something like cat to-do, and I can pipe it into word count application, and I say, show me how many lines. And it says, wow, you have one line there. Sorry for this, right? So it kind of allows me to compose. If I have multiple applications like cat, which shows something on a screen, like what's inside the file. If I have word count, I can kind of build tiny programs. Typically, those programs are like one line, although I have built like hundreds of lines of shell scripts back in the days. It's not pretty, but it's kind of like Python in a way, but very, very dumb and very, very awkward and very, very inconvenient Python. But really, it's more like a programming language. And so what I wanted to say that shell is kind of an interpreter which allows you to type tiny programs, which allow you to use compose functionality of smaller programs which you run on, which you have on those machines, right? It's kind of like allows you to, it enables this ecosystem of tiny programs. It's almost like an Android, which says, okay, look, Android comes bare bones, no apps or minimal apps. The less apps, the better, right? And then you install your own stuff and they somehow communicate with each other. Not so much, but sometimes you can say, look, I kind of print, and then a printing up comes up. So it also allows you like to compose, or everything is driven by fingers, right? And in ChatGPT, maybe you ask a query and who knows, maybe it just does some information retrieval and tells you who, whatever your instructor in the operating system class is, right? So it's all kind of languages. And the shell was this primitive language, which was designed, but they like 40 years ago, it wasn't that primitive. And the reason they wanted this language is that they said, okay, we want this interface which allows us to like, in this example, you print like all the files in an x86 folder on the screen. And it prints line by line. And you ask a question, why is that? Why do we do this? Why not to show it like as some kind of icons on the screen or something like that? But of course, primarily reason was that really the hardware which they had back then was just a printer. So here's this creators of Unix, Ken Thompson, Dennis Ritchie, working on this PDP-11, 1970. So it's what, like 50 years ago, 55 at this point. And they're programming potentially like an operating system or something. And that's the interface. You type, it prints something back. It's convenient. You know, if you say ls, it will print you like 3 lines of stuff, right? Then the first terminals they looked like that. They were more glorified than printers, but kind of like printers, which just can print very, very fast on the screen, right? So they didn't have a capability to quickly scroll with fingers or anything like that, right? Or ask your personal assistant to do something for you. But they came up with this tiny little language. And they said, okay, they were thinking of this system as a language on top of a kernel. And if you have this language, then you can compose different things. It's almost like running libraries in Python. But again, back then they didn't have Python or the ecosystem of like hundreds of thousands of libraries. They came up with this. They say, okay, look, shell has a command prompt. Sorry. Where is it? It offers you to type something in, similar to a Python thing, right? You type ls, it prints all the files in a folder. And ls is a program. So it's like an app on your phone, which maybe count your steps or something, right? Back then, no one was thinking about counting steps. Word count, you think, okay, why do I care about word counting? Well, sometimes, you know, if you submit an article to a journal, they say, you know, 400 words for an abstract or something. So also useful, right? So someone writes this word count. It's not you, it's an ecosystem. So like someone on the other part of the world writes word count. It takes some arguments. It counts the words. It says there is 85 words in ls.c, right? And if you want to combine them, shell allows you to do that in some not ideal, but meaningful way. And it kind of makes sense. So this enabled like a rich ecosystem of small programs combined together, right? And the operating system interface, which they envisioned back then, was kind of designed to back up this shell, although it's not like super far from what we sketched on the board. If I ask you a question, so in terms of what shell is it something special compared in the ecosystem of other programs? Is it special or not? What is a shell? Like, remember, I'm drawing my operating system kernel instructions. Where is shell? It's just an app running. So in fact, there's nothing special about it. So it's like typically when you boot, you first boot into something what is called an init process. Depending on sophistication of how you want to sign in, it might ask for like password, but after that, it starts a shell for you, right? And it will be like, init will be running as a program, switching back to the OS. Init will start another program, shell will be running, right? Stuff like that. But it's nothing special, just a program. In fact, you can run multiple shells, and I'm still running in somewhat archaic bash, but everyone who is like young will run something like what is called a fish shell, right? So I should switch as well, right? There are multiple shells. They implement slightly different languages. So I would prefer something like Python. Will be like way cooler, right? You know, any libraries, you know, you want to run. So it's a normal process, as I said. Kernel started in x86, shell is created after the init, which is the very first process which you boot into, right? And from shell, you as a user can start other processors. Or if there is like some automatic process which start when system boots, they can start as well. And what happens when you, inside the shell command prompt, you type something like wc-l space ls.c. So asking to count the lines in ls. So what happens is shell, as any other interpreted language, will parse this string, would say, okay, like there is like 3 tokens. The first one, by convention, is the name of the application we want to start, then some arguments, like in fact, like -l and ls.c are the arguments. What it will do, it will start using this system call, which we came up with, create process. Although on this interface, it will be slightly different, but essentially it will start a new process, which is WC. We'll pass those 2 arguments, -l, ls.c, and we'll wait for the output of WC, right? And essentially, it will wait for WC to finish, like wait for it to exit. And after that, we'll print the command prompt again, asking you to like here, okay, do you want to, what is that next thing you want to do, right? And you can, if you start something like a word processor here, I don't know, something like Vim, well, then you will be typing in Vim for hours maybe, and then you exit and Shell will ask you again, what is it you're trying to do? Like most of you did it, right? So not super hard. So, okay, so now let's go into the details of how they wanted to build this, like the interface, the operating, like concretely operating system interface to make sure that Shell is running and everything else is running. So we'll start with this console and file IO. We correctly guessed that we need a collection of system calls which allow you to open files. And this is the signature for the open system call on x86 operating system, which is, the signature is very similar to the one on Unix as well. And essentially, an open system call takes a pass to a file and some flags, like a read-only, it can have read and write, it can have a flag create, and returns a file descriptor. That's how they wanted to see it, right? They say, okay, you return a file descriptor. In a good programming language, you would say, look, it's not, file descriptor should be a pointer to a file, right? And then you can use this pointer to like say something like fd.read maybe, right? Well, they had only C back then. So they said, we'll return a file descriptor. So what is this file descriptor? Does anyone know? What is it?
It's an int.
It's an integer, it's a number. And what's the semantic meaning of this number? What do you do with this number? Or how does the operating system use this number? Do you know? Correct. It's kind of like a name. A name given to you as an integer. It can be 0, 1, 2, 3, and so on, until some max number, which operating system configures. And you can later on say read from this file descriptor, providing a pointer to a buffer and a size. And instead of this file read, the operating system will, like if it's a pointer to a buffer, will read something from a file into the buffer, right? It allows you to name a file. But how it works is the following. So operating system maintains an array, which it calls a file descriptor table. And essentially when you say open a new file, giving like a human readable string as a name, the operating system will scan through this array in order and will find the very first unallocated entry. And in this example, it's entry number 3, and it will say, look, I will create a data structure internally in the kernel, which will represent this file. And it will be used by the file system code to make sure that you can later on go and figure out where the file is on disk and stuff like that. It will maintain metadata about the stuff, the file on disk. But for you, I will give just the number 3, and you can use this number 3 to index back into this array and make sure that you can read from this file, and then you can close this file or delete this file, right? Well, it's a design choice, but it's not bad because it doesn't matter whether you give a number here or you give some kind of a string. you just need to build, it's kind of like a pointer, but you cannot allow a direct pointer. Do we understand why you cannot allow a direct pointer into the kernel? It's kind of a protected pointer, right? Because logically it's a pointer. It's like, if I erase everything on this screen, this file descriptor always, like, I will draw it in dashes. It points to a file, but it points in some protected manner. Like, for example, if you say, well, I will make up, maybe another process opened another file. There is no way for you, sorry, wait, let me do, is there like Control Z here? Nope. If another process open another file, and maybe this file has your credit card, unless you perform open, and maybe there is some access control check that only like some other specific process can open a credit card file, no matter which number you make up here, so you can put 55, and maybe there's even 55 entry in this array, but it will never be pointing to this file, which you cannot open, right? So it's a protected pointer in a way. You understand how it works? You will see more of it. Like it's almost like a distributed system, right? So because you say my user level, which lives in this ring 3, and my kernel, which lives in this ring 0, they cannot share pointers because we don't trust the user, because the user can say, look, if you just give it a direct pointer to a file, like it can like change it literally and point to a different file. So they introduced this like intermediate mechanism which checks that, okay, you can only access pointers which you previously opened, and if you have some access control checks for what, like, you know, like who can open which files in the system, you can only open maybe files in your home directory or stuff like that, right? Agree? Makes sense? So that's what they came up with, and it's kind of like, it's okay. Any questions about this? Each process will have its own file descriptor table. So for example, if we have like 2 processes, and you know, one is cat ls.c, this one wc minus l on wc itself. Each process will have its own file descriptor table. Of course, the numbers will overlap. Each of them will have a 0. And here, this one is opened wc.c as file descriptor number 4. There's a pointer here. And this one is as file descriptor number 3 points to file ls.c, right? That's how it's organized. So each process will have its own file descriptor table. Agree? Any questions? Okay, so, and the way we like work, they also had this kind of inspiring idea, also almost like a prehistoric idea from the programming languages. They said, okay, or polymorphism or something, like they say, okay, in our system, everything will be a file. It's kind of like a dream. You say, if I have a network card, I can open it and I can read and write into the network card. Or if I have a graphical user like a GPU, then I can open it and read and write into it through a file interface. So which means that if you say open something like dev, which is like a device subsystem, something like a GPU, you will be talking to a GPU through a file which you open here, but with this read and write system calls. If you open something like open, I don't know, again, dev, something like a NIC number 1, where a NIC stands for network interface, like a network card, then you will get a file descriptor which will allow you to send packets on the network, right? It's kind of elegant. So in practice, it didn't live to the expectation. Some things could be elegantly abstracted as files, like a console and the files themselves. But network, you know, you have to set some, you know, connection speeds, IP addresses, stuff like that, kind of quickly falls apart. And so not everything is a file today, but they wanted it, right? And to some degree today, like not today, in x86, in x86, actually everything is a file still. So it's kind of this idealistic way. And they came up with this elegant interface. It's kind of like, you know, in a programming language, you would say, I open the file descriptor and it has a, I don't know, if you in terms of C++ or Java, it's an interface. In terms of Rust, it's a trait. And the trait has like those, you have like open, read, write, close maybe. And they had the same philosophy, although they didn't have a language to kind of run underneath. So everything was like, it's almost like you're passing a pointer to an object as a first argument in the system call, right? So they have open, they have read. Read takes a file descriptor, a pointer to a buffer in memory where the data will be read, and the size of this buffer. Write takes similar stuff, a pointer to a buffer in memory from which the operating system, and a size from which the operating system will take the data and write it into a file, right? That's their interface. Kind of elegant. Like I cannot say that they screwed it up much, right? And it worked. And they said, okay, look, but we will take this idea even further. They say, we will come up with a convention for how to start a program with default standard input, standard output, and standard error. And they said, okay, if we start a program, the convention will be that file descriptor 0 will be pointing to standard input. File descriptor 1 will be pointing to your standard output. And file descriptor 2 will be pointing to standard error. And essentially you say, look, like, which means that you can start a program, I don't know, like cat, for example. And cat can, for example, read from a file, or it can read from a console. So how to illustrate this thing to you? Let me just quickly do it. I mean, I don't know how much time you spent in a shell, but let's just, so if you do cat to do, it says, okay, it's empty for now, but how do we do this? What I wanted to say is the following. So cat, right now, cat was printing something on a screen, but if I use this symbol, which stands for input redirection or output redirection, I can say, look, take to do MD, but output it to the DDD file. And now I have this DDD file here. And if I cat it, it will contain the, like, obviously, it just, instead of like printing on a screen, what was done with this symbol, the cell itself, before starting the cat, changed its standard output from the console would bring it back to the shell, to the file, right? And they said, okay, look, it seems to work very nice. So you can do something like take an input from, it means take an input from to do, put an output, like let's put an output on a console, or you can put an output in the DDD2, for example. And then DDD2 contains empty for now, right? So what it means is that it allows you to, I will explain it in a second a little better, but it allows you to like change the input and output for the program without changing the program itself. It's kind of like the program itself says, okay, by default, I will be running on standard input on a standard descriptor 0. And whatever is there, I will just simply read it, and I will simply write it as standard output, file descriptor 1, right? So let me show you. This is maybe somewhat simplified, but not much, implementation of cat utility, which I was running in shell from x86. So literally what it does, it says, I will be running an infinite loop. I will be reading from standard input, file descriptor 0. I will be using some internal buffer of 512 bytes, which is buffer here and a size of buff. And if I read nothing, then I will break out of this loop and exit. If I got a negative number as a result of read, it means that it's an error. And I will print an error to the standard error, saying, okay, I had a read error, and then I will exit. But if I read everything successfully, it's not 0 and not negative, I will simply write it to the standard output, the same buffer which I read. And okay, it can happen that I didn't write the whole thing, and then I will say, look, it's a write error, and then I will exit. But if this is an equality, then I will continue and read more from this file, right? There is certain elegance in it, right? So you say, look, you showed us cat, it prints something on the screen, but maybe it's a little magical that you can write it in whatever, less than 15 lines of code. So it's the power of this interface. By making this convention that 0 is the standard input, 1 is the standard output, you immediately enable this paradigm that, you can write those little simple tools, right? So they kind of like, I don't know, today you think of, I don't know, like some natural language processing, and you think of them as like, I don't know, maybe data flow between different stages. And this is one stage, it takes an input, puts an output. So they had the same idea, but they only had strings back then. So it didn't have any like large amount of data, right? You got the point. So this is the kind of the elegance, right? And the way it works is that when the program starts, shell itself, and we'll talk about it next time, but shell, which parses my cat redirect output into like DDD, or maybe like in this specific example, we are redirecting input. So I say cat, take input from whatever the file was, to MD, right? So it parses this symbol and says, okay, the guy who who typed this command wants me to start cat, but in such a manner that the standard input will be redirected, will be taken from, not from the console, but from the to-do, right? And by the time it starts the cat here, before it starts, it makes sure that 0 is opened. And instead of pointing to the console, it will, I'm sorry, I hope I had a slide. This one will be pointing to to MD, right? And then cat runs as normal. It doesn't know that something like that happened because the shell set up the environment. Shell, which was a programming language here, parsed that symbol and said, okay, your standard input will be to MD, right? Agree? So that's nice. So kind of matches our expectation of a nice programming language, although it's very, very primitive. Okay, so let me stop here. And on Tuesday next week, we'll start discussing the interface, which allows us to create processes and stuff like that. So thank you. I will see you next week.